excited to be here again, and especially now that I've also been getting a chance to learn from all of our speakers over the last few days. It's really fun to get to tell you something else. So today I am going to talk to you about polymer networks. And again, I want to put up some references in case you want some further reading. So I like this book, Polymer Physics, by Rubinstein and Colby. Molecular Driving Forces is a really interesting book. It does some really useful calculations, but it works very hard to have very self-contained math, and so it's a really nice resource. And for some of the more intuitive explanations, I think there is something to be said about the really the classics. And so I also will put up Florey's book, Principles of Polymer Chemistry. Which is from 1953. All right, so what is a polymer? I'm going to follow Vincent's lead for the first lead up, and I'll do a numbered list, and then I'll lose the thread pretty soon, I think. But the first question we might want to ask is, what is a polymer? And for this, we can define it quite generally. It's some sort of molecule that is made up of many repeating units that we call monomers that are bonded together. That's fine, but you might also have the question, why are we discussing this in the geometry, mechanics, and physics of growth workshop? So I would like to convince you that I think this is a very central topic, actually, to a lot of the things that we're interested in here. One that is perhaps the most concrete reason is that polymers are really important in biology. They're something that comes up really anytime that you're trying to, have structure, convey information. It's hard to think of a process in biology that doesn't involve polymers. So polymers are central to biology. Hadrian introduced one, I believe you said it is the most common, what was it? Most abundant biomolecule. Okay, so lots of cellulose out there, but also starch, protein, DNA. Understanding the mechanics of all of these things requires polymer physics. I think it's also really interesting when we're thinking about how are we modeling growth and how are we thinking about the microscopic picture of growth, because in polymer physics, what we're actually doing is we're constantly taking a microscopic picture, perhaps a little cartoonish, and then we're getting continuum behavior out of it in many cases. And we're able to describe things that have a lot of superficial similarities to growth. In particular, I'm going to focus on how do we use these arguments which are really all entropic arguments. How do we use them to understand macroscopic swelling? And there's a lot of interesting comparisons, I believe, to be drawn between swelling and growth. They're both these processes where there's an uptake in mass and there's a change in shape. But in polymer science, we have a little bit more thermodynamic certainty about what's going on. We really can make arguments. And so thinking about where those might fail and where those might succeed for growth can be really interesting. So I think that I think polymer network swelling is kind of the ultimate comparison to a lot of these growth questions that we're making. This can be sort of the null model that we might want to compare things to. So in words, polymer swelling, which is our ultimate goal, although I would be surprised if we got to it today. Ultimate goal gives an example of micro to macro. And it also is a nice non-living analog system for exploring key topics. All right. And then my last number, and I think at this point in my notes, I lost the thread. So everything else in the lecture is going to be 3, which is how can we describe the mechanics of polymers? And eventually we're going to build up to polymer networks, but we're going to start today. The majority of today, if not all of today, will be just on polymers themselves. So I will start with an observation, which is that many polymers are elastic. Many polymers are stretchy. Why? And I will argue that the answer is quite generic in this case, and it is because of entropy. So I thought I would now, I know I'm the first to go in the morning, so I'm going to ask you all to do a little exercise that's give you a little bit of an intuitive sense. This is a very toy problem for the kinds of things we'll be talking about today. So what do I mean by entropy here? Well, to answer that question, what I'm going to ask you to do, and I'm only going to give you like 10 seconds to do this, because I think this is one of those questions that's fun if you do it fast and not so much otherwise. So I'm gonna set up the question, I'm gonna start the clock, and then I'm gonna have you all tell me your answer right afterwards. So it'll be like a flash example problem. So here's our setup. So here is a monomer that is attached to the wall. And it has some length, B. And we want to attach 2 more monomers. And we can do that by either having them go straight or 90 degrees. But they can't overlap what they've already done. And so you're attaching to this, you're attaching a bond to this last one. And I want you to now take, maybe I'll even give you 15 seconds to answer the question. How many ways, so if this is X, how many ways to have, with adding 2 more monomers, a length of B, 2B, and 3B? All right, go. Is the question clear? Yeah. Oh. So in case it's not clear, I'll give you one for free of length B. This is length B. All right, time's up. All right. How many ways are there to make something of length B? I count 2. See, this is one of those questions. If I gave you time, you would all get it right. But I got to keep you on your toes. How about 2B? Okay, I count 4. I'll show you all these in a second. And 3B, it's just the 1. So here's my count. So for B, for length B, I have this configuration, and then I also have this configuration. For these are both length B. For length 2B, oh, I don't want them to hit the wall. Okay, so I'm changing. Like this is it's only able to go straight or 90. It could go backwards, but not with 2 without hitting the wall. Yeah. Okay. So now I see that I really made this a hard problem by not defining it well. So here's 2B that I can count, and then I have 2 up, and I have 2 down, and then 3B. I think everyone got this one. So the thing that I want to emphasize from this problem is that there are, in this case, and also generically, there are many more ways for a chain, if you don't care about anything other than the number of conformations and this horizontal extent, there's many more ways for a chain to be somewhat compact rather than fully extended. And this is really underpinning of saying that entropy is driving elasticity for polymers. So I'll write that down. There are many more ways for a polymer to be folded rather than fully extended. And so if we're thinking about this in terms of entropy, we can define entropy in terms of the number of the entropy of a certain state will be related to the log of the number of microscopic configurations consistent with that macroscopic state that we're interested in. So in this case, for this definition, the entropy of state length 2B would have 4 microstates that correspond to it. The entropy of length B would have 2, and the entropy of 3B would have just 1, which would give it an entropy of 0 when you're considering this state. So using this definition, the intermediate extent in this toy problem has the highest entropy. And so now here is the key, I don't know, backbone of polymer physics, which is that it's often reasonable for us to assume that all conformations for a polymer have the same energy, in which case, which actual conformation it's in is determined only by the entropy. And that means if you're imagining a polymer that is sampling all of these different states, roughly equally, it's just going between all of these different states and thinking, which one am I going to be in? You will, on average, experience that if you pull it straight, it will retract back. Because entropically, this state is preferred, and this state is very hard to reach entropically. And so if energy is unimportant, system will be contracted more than it will be straight. More. And if you pull a polymer, it will retract. And this is, again, I'm just hopefully making this point very clear, and then we will do a more elaborate model with this, but this is entropic elasticity. Elasticity. Okay, any questions on the setup here? Okay, so what model are we going to use to do this exercise more carefully and for things that can be extremely large? As I'll mention a little later, the largest polymer that at least Rubenstein and Colby know about is 10 to the 10 monomers long. And so these things can be very, very large. We're not going to be, even if I gave you more than 10 seconds, we're not going to be counting those conformations. So we need a way to systematically figure out the number of conformations of these polymers. And the way that we are going to do this is using random walks. So random walks are a general, yeah. On average, yeah. Was that your question? Oh, yes. Sorry, that is exactly what I mean. When you pull polymer and release it, it will then retract. Thank you. That was unclear. If you pull a polymer and release, it will retract. Thank you. All right. So random walks are a general mathematical object. They're used for all kinds of things. It is a stochastic process. Where a path is taken with random, uncorrelated collisions or turns. And this is an extremely broadly applied mathematical tool. I mean, some famous applications of it include if you are trying to solve problems like if you're spinning a roulette wheel, will I be able to go home with any money in my pocket? This is a classic time you would apply a random walk. If you're asking questions about how do genetic boundaries in space navigate, they both perform a random walk in terms of frequency space. And also, if you have a spatial system, they may also perform a random walk in physical space. There are many, many examples, but perhaps no example is more famous than that of Brownian motion. So Brownian motion is the random motion of a large molecule because it is buffeted by smaller molecules in a bath. So let me actually just draw a picture. So we have a large particle in something like a solvent, and it will take some sort of path like this. This is a perfect example of a random walk. And for this lecture, I was so inspired by these beautiful examples of how much we can learn from plants, from both Joel's talk and Hadrian's talk. So I had remembered that Brownian motion was discovered by a botanist, but I dug a little into that paper and to give you a little more of a historical picture of this. So Robert Brown was actually a Scottish botanist. He never had a degree, actually, but he became very interested in, he became well known for cataloging Australian plants. He went on one of these long trips. And then, maybe that was his main focus, but he had always this big interest in plant physiology. And he was one of these early folks to really start playing around with looking at plants under a microscope. At the time that he was doing this, which was the early 1800s, microscopes were relatively new. It was a cool new tool, like the way that Joel is looking at plants with tools that no one's been looking at plants with before. This is Robert Brown was also doing the same thing, advanced imaging. And so what he noticed was that when he put pollen particles in water and he looked at them and he saw this really weird jittery behavior, right? And his first thought was like, oh, well, these must be alive. I'm looking at a plant and they're moving around. They're obviously swimming, right? So, and other people had actually noticed sort of jittery behavior and similar things before. And I think most people, the Romans actually had looked at dust particles in air, but people had sort of waved these things away and not attributed it to Brownian motion. They were like, oh, it's air currents or these other things. And so, but Robert Brown, he was like, all right, well, I'm really going to nail this. Let's figure out if I want to see if this is something that is alive, I have to show that it's not there and something dead, right? That seems like a very rigorous way to approach the process. And so first thing he thinks is, this must be something weird about the particular plant I'm using. So the plant that he was using was Clarkia pulchella. And he was like, oh, is it only in this plant? And so he tried all these other plants, very systematically characterized them, and it was not only this one plant. So, okay, all of these plants are showing this. Okay, so it's not just one plant that's swimming. And then he did also something that Joel did. He's like, well, let me test this on a dead plant. Let's see, that seems like a good way to perfectly control for the particle size. And then, of course, they won't be swimming then. But the dead, so let me structure this in the right way. So let me say instead of if plants that were not Clarkia pachella, and yes, he saw Brownian motion. Dead plants, yes, he saw Brownian motion. And he said, okay, maybe the plants weren't dead enough. These were only dead for one day. So then he found a 100-year-old dead plant. And he was like, well, this one's much more dead, so it surely won't do it. So then he looked and still there was Brownian motion, and he was like, okay, well, let me try like London soot. So we tried all this organic matter that was surely not going to show this, but was clearly related to plants. And again, and he narrates this very clearly in his paper. It's very linear. So he tries soot, and yeah, he still sees Brownian motion. So he's like, okay, I have to go more dead. Let's try something inorganic. So he looks at minerals. And yes, once again, he sees the exact same thing. And then this, all this is happening. This is published in an 1828 paper to give you a sense of the scientific community at the time. And so he says, okay, I've tried it on the most dead things I can think of, but there's one thing that is more dead than any of these things that I still can try it on. Maybe this will finally get rid of Brownian motion. And it was a piece of the Sphinx from Egypt. And this was to him the primary most dead thing that science could find. And therefore, when he saw Brownian motion in the Sphinx, that's when he knew that this truly was not alive. So anyhow, it turns out that this was not something that was understood in Robert Brown's lifetime. It was actually Einstein who made the model for this. And now we understand it to be related to this random buffeting of these microscopic particles, and it's now really a foundation. So when can a polymer be modeled as a random walk? So when is a random walk appropriate? And a random walk is appropriate, really whenever we can imagine that the polymer is, every step is a different unit of the polymer, and that they really are taking, the polymer itself in space is taking turns that are random and uncorrelated with each other. That is when you want to use a random walk model. And so it is, again, related to this assumption that I came up with before, which is that energy is really unimportant for the system. You can assume that all conformations have approximately the same energy. And then, well, actually, I guess that approximation comes in later with what we're going to do with it. But we want the turns to be uncorrelated, which also means that we shouldn't have any interactions between any of the units along the chain, because these models assume that you're, almost like the most concrete way to think about this is walking forward in time. So if you're now imagining a polymer chain that actually has a physical trajectory that it is tracing out, you don't want it to be interacting with itself, or else it will no longer look like a random walk, the ideal random walk that we'll be working with first. So a random walk's appropriate when there are no interactions between monomers that are far apart on the chain. No interactions between monomers far apart on the chain. Even if they approach each other in space. This does not actually mean that we need to assume that our polymer is making such sharp angles as I've drawn here in this caricature of Brownian motion. What is totally consistent with these random walk models is considering, say, a linear polymer, which is the most straightforward application of these ideas. And then saying that, perhaps the individual monomers are not the right step size, so to say, if I'm trying to build this random walk. Perhaps what we need to do is imagine a slightly longer length that is called B Kuhn length, where beyond this point, the direction of these neighboring bonds are now uncorrelated. And so if we're looking at a slightly coarse-grained scale, a polymer like this could still be very nicely described as a random walk, even if you insisted on every step truly being the addition of a monomer, that might not be actually a very good model. All right, now that we've set this up, let's derive some results. We are going to work on a square lattice. On a square lattice, this is going to make the calculation much easier, but because of the central limit theorem, all of the results that I'm going to derive will also hold. It's surprisingly hard to break a random walk. You can do it, especially if you're drawing step sizes from interesting distributions, but as long as we're keeping sort of even steps and we're just allowing it to happen in a continuous space or a continuous angle, what I'm saying will all still work, even though I have the luxury of getting to derive it in this simple system on a square lattice. So central limit theorem makes this robust, since we are really just adding up a bunch of random variables. All right. What is the first question we want to answer about a random walk? Well, I'm going to go back to this toy example once again, which is that we ultimately want to connect this to elasticity. And so the thing that I have said so far that is the most closely related to elasticity is this last statement. If you're pulling on a polymer and then you release it, the fact that it's going to retract seems to be the right way to approach taking this stochastic model and bringing elasticity into it. So let's dig into that a little more quantitatively. Let's ask the question, what are the statistics of the end-to-end distance of one of these polymers? And then that will give us essentially the advanced version of this toy calculation, and that will allow us to understand what's going on. So that will be our main goal, statistics of the end-to-end length. And so here are the quantities that we're really thinking about. So if this is a polymer where we have n monomers, where our Kuhn length is going to be B. B is step size, I'll just say. Then the contour length of the entire polymer will be L equal to NB. But in reality, now I'm not going to move to this, I'm going to move to the square lattice in a second, but for these pictures, I will keep drawing. Let me get rid of this one actually. So my goal was to draw this many steps in this polymer, which I think is not quite right, but this is the idea, is that if you have all of these different end-to-end lengths, all of these different vectors, all these different steps, you will have a distance between the origin and the end of the chain that is going to be what I'll call this vector x, which is our end-to-end length. And this will, except in the most extreme entropically disfavored situation, be much shorter than the contour length. we are instead going to work, as I mentioned, with the square lattice. So you can think about something that is instead stepping on a grid. And I'm drawing this time to emphasize that unlike the example that I gave you, we are not going to require that this polymer does not overlap with itself. We'll talk a little bit about the effects later, but for a first step, we are going to say that overlapping is completely fine, and we will not worry about it. Okay, so now that's quite a long polymer. Let me draw its end-to-end length here. Again, this will be my X. All right, so I mentioned yes, so I also want to say here, I meant to say, when there's no interaction between monomers that are far apart on every chain, even they approach each other in space, when does that actually occur in reality is a question that you might want answered. And this is pretty good for linear polymer melts and concentrated solutions. And concentrated solutions. And the reason for that is because the interactions are typically screened by being in such a dense environment. All right. So the quantity that we now are set up to find is going to be P of X as a function of N. This is the probability that a chain starting at the origin is going to have end-to-end distance that is actually the magnitude of X. Have an end-to-end distance of this magnitude of X after N steps. So probability of a chain at the origin having an endpoint X away after N steps. And the thing that we can do to significantly simplify this is to recognize that in a system like this, we have a random walk that we can actually decompose into two different random walks, right? So if I'm not worried about time, I'm just, I have, one person here counting are my steps left or right, and one person here counting are my steps up or down. If you were ignoring the other process and not worrying about the pauses in between these steps that you might take, the statistics of how much left and right you go and the statistics of how much up and down you go, those will also be random walks. And so we can decompose this function P of X times N. Actually, I changed my mind. We'll bring this back later, but I think I won't put my magnitude here. P of X of N, and this is the product of as many 1D distributions as we want, depending on what dimension we are in. So this is XD to the ND. So these are three independent, or D independent walks. The key is that they have different numbers of steps, right? They don't necessarily all have to have N steps because we randomly choose which dimension we're going to walk in. So D independent 1D walks. All right. So that means that's good for us. We only need to find the statistics of one of these factors, and then we can have the statistics of a random walk in any dimension. So how do we find this? And whenever we're working with a discrete system and our goal is to find the entropy, your first thought should be, I better be counting something. This is going to be something combinatorial. So we want to apply some combinatorics. So to figure out if I am trying to be a polymer and I'm taking n, if I'm just going in one direction, one dimension, and I'm taking n steps, this is just a purely 1D walk. This is the same as saying, if I have n possible choices, how many possible paths exist where nr of them are to the right? If we are able to split the total number of steps into the steps to the right and the steps to the left, these are going to be convenient variables for us to work in as we're counting the total number of paths. Because what we're doing is essentially, this first exercise is we're saying how many paths lead to us being at these different endpoints. So this ends up being, so n steps, how many paths with nr steps to the right. And these are really the same variables because our endpoint x can be expressed as the number of steps to the right minus the number of steps to the left times b. And because n is equal to the number of steps to the right and the number of steps to the left summed, that means we can also express, I can actually do this out. That means we can also express NL and NR in terms of X. So if we know that N is equal to N plus NR, and NR plus NL, then we can plug this in essentially here. So we can plug in, let's solve for NL. So let's plug in this expression, N minus NL into NR. And we have X over B is equal to N minus NL minus NL. And solving for this, we find NL is equal to N minus X over B over 2. And similarly, NR is equal to N plus X over B over 2. And now we have set ourselves up very nicely that we can now do this in one fell swoop. The number of paths, omega, for NR steps to the right is just going to be N choose NR, which is N factorial over NR factorial, N minus NR factorial, which is equal to N factorial over NR factorial NL factorial, which is also equal to N factorial N plus X over B over 2 factorial N minus X over B over 2 factorial. And if we want to now go to the probability in 1D of xn, all we have to do is divide by the total number of paths that exist. And because we're just in 1D, that's quite straightforward. Sorry about my messy handwriting here. That's quite straightforward to figure out. It's just dividing by 2 to the n. That's how many total paths there are, and that's how we're turning this counting argument into a probability. So this would just be n over n plus x over b over 2. I won't write out all the factorials again, times 1/2 to the n. That would give us a probability. As an aside, you might notice here that it's quite easy to extend this to a biased random walk, which is something that has many, many applications as well. So P1D bias would use the same counting argument. We would have n over n plus x over b over 2, but we would not be dividing it by 2 to the n, the total number of paths. Instead, we would be weighting every single step according to the probability that we take it. So we would have P to the n plus x over b over 2. This is P to the nr. This is the probability taking nr steps to the right. And then Q would be another probability of n minus x over b over 2. This would be step to right. And this would be step to the left. Okay. Now we are going to start moving this to more of a continuum picture, but I can pause here and take questions if there are some. Yeah.
Can you say a little bit more about the linear polymer melt situation? Because I can see the highly concentrated limit is to be valid, but can you speak a little more about linear polymer melts?
The idea is that you're screened from yourself by the presence of all of these other chains that are also in the linear polymer melt. So a polymer melt is something like silly putty, which is it's not in solution, it's all together. There is another limit in which this is what we're deriving is this ideal chain model, and it's often in contrast to real chains. And these are reasonable physical scenarios in which you would get an ideal chain, but you would also get an ideal chain. I don't know if we'll have time to do it now, but there is also something called a theta temperature, where you also will always get this random walking behavior. You're perfectly in between a good and a bad solvent. You also always see this behavior. Yes, I don't have I think I would probably refer you to Rubenstein for more information on the specifics polymers beyond that. All right, so let's now move this to a continuous probability distribution, which is really what we want, because we're going to apply the, we want to be looking at these chains that are these polymers that are very, very long, and so we want to be working with this continuum approximation. And so what we're going to do is apply Stirling's formula. This is one form of Stirling's approximation. I'm going to keep this square root term because this will lead to this thing normalized. And now I'm going to take this expression and I'm going to apply this formula everywhere I can. So first, actually, I'm going to take this expression divided by 2 to the n. So I'm actually going to take this 1D probability. And this is equal to these 3 factors. And now this will be n to the n, e to the negative n, 2 pi n, divided by, let's have that factor of 2 to the n here. This is just Stirling's approximation on the top, and now we'll do Stirling's approximation on the bottom. We have n minus x over b over 2 to the n minus x over b over 2. Long denominator here. We have this e to the n minus x over b over 2. And we have our square root term, I n minus x over b. We have that extra factor of 2 now coming from the definition. Now we have the terms, so those were the terms from the steps to the right. Now let's do the terms for the steps to the left. We have n plus x over b, the opposite. I did the left steps first, now I'll do the right steps. N plus x over b over 2 to the n plus x over b over 2. E to the negative n plus x over b over 2. And the square root of pi n plus x over b. All right. Now, some things will nicely cancel. All these exponential factors will cancel. And this will become, this is an approximation, and this will become approximately 1 over 2 to the n, square root of 2n over pi n minus x over b, n plus x over b, n to the n over plus x over b over 2, and plus x over b over 2, and minus x over b over 2, and minus x over b over 2. Oh, how will this possibly turn into an incredibly simple form? We will see. So all I've done so far here is assume that n is very large. So there is another approximation that I'm going to be able to make. Does anyone see what it is? This is clearly not viable. I'm not going to be able to work with this. So I heard some whispers. I am going to be very comfortable assuming that x over b is much, much less than n. So that is the same as this sort of throwaway comment I made over here, which is that for a sufficiently long chain, I'm always going to expect the end-to-end length to be much shorter than the contour length. It's the same as saying it would be very unlikely for this to be ever stretched all the way out. And so therefore, I'm also going to be able to assume that this parameter is really small. And that's going to allow me to do a lot more simplifications that is almost going to get me all the way there. Oh no, this is our last step. This will get us all the way there. So in order to do this approximation nicely, I'm going to take the log of both sides, the log of the right side, log of both factors. And I will just sort of indicate this. So the log of this, let me move this over here, actually. I want my 2 to the n here. So the log of this term in this limit, in limit of x over b is much, much less than n, dropping terms of order 1 over n squared. This term just gives me 1/2 log of 2 over pi n. And then this term, I'm going to do the same thing. I'm going to also do this. I'm going to take the log of it. I'll take this limit, and then I'll drop terms of order 1 over n squared. And what this gives me is a term that is negative x squared over 2b squared n. So this is, on the left-hand side, this is log over omega to the n, which is really our 1D probability. So now, what we can do is we can exponentiate both sides, and we find that the left-hand side will just be our probability distribution, and this will be 2 over pi n e to the negative x squared over 2b squared n. This is a Gaussian. This is what we have found, is that our random walk will ultimately give a Gaussian distribution for the end-to-end lengths of these chains. We are not quite done, because if you look carefully, you see that the units are a little bit off. We ultimately want x to be a continuous, we want this probability distribution to be a continuous probability distribution, so we should be able to integrate it over space and get a unitless number. So we need to actually recognize that what this really is here is not just the probability in 1D, it's the probability in 1D times a little window delta x. And the window delta x ends up actually being, well, as you might expect from looking at this picture, the window of this 1D walk, it should be related to b, the size of our steps, right? It turns out to get the normalization right, you actually have to recognize that this is 2b. And what's the reason for that? The reason for that is that it's impossible to be taking an even number of steps and ending up at an odd location, and vice versa. If I'm walking a total of 6 steps, I will either be at 0, 2, 4, 6. If I'm walking 5 steps, I'll either be at 1, 3, 5. And so as a result, this window is actually equal to 2b, because that is sort of the coarse graining, that's the finest level of resolution that we can have in this system. And when we plug that in, we finally get our 1D normalized probability distribution, which is the square root of 1 over 2 pi nb squared e to the negative x squared over 2 nb squared. And then without doing any work at all, we can now take this and get one of the central results for random walks by just looking at the variance of this Gaussian. So the variance of this will give us this average of x squared, and this will be exactly nb squared. And if you have seen random walks before, this is probably what you're most familiar with. Looking, oh, did I do this wrong? No, this is right, this is right. No, it's not right. Where did I go wrong? I went from b squared n. No, that's right, that's right. I got confused. B squared n, yes, okay. So if I look at the root mean squared of x, it goes as the square root of n. So this is the classic result for diffusive motion, that it goes as square root of t. This is the same idea if you are now thinking about, instead of time, if you're thinking about the number of steps that you're taking, this is the same statement that you might be most used to hearing about diffusion, which is ultimately related to these random walks, and you can derive the diffusion equation using these arguments as well. It's not a terribly far removed calculation from what we've already done. I will make one more comment about one dimension. Actually, I'll erase these boards, and then we'll talk about how this extends to 3 dimensions, and then what this actually means for polymers. And then we are going to turn this into network elasticity and find out that this is actually neo-Hookean. Yes. Yes, so the idea here, so one way you could approach this if you wanted to is you could just say, oh, this isn't normalized, let me normalize it. That would be a totally reasonable way to avoid thinking about the 2B. If you're like, oh, it's getting weird with the limits, that would be fine. I like this argument of sort of recognizing that, and depending on this, if n is odd or even, you have a limitation of the possible endpoints that you can be. And so what we're really doing here is we're taking this discrete probability and turning it into a continuous probability, and we're talking about the window this is what is the chance that this is the window that my endpoint falls within, is how we're going from this discrete to this continuous probability distribution. And the smallest possible window is going to be 2B, because you have this restriction of it can either only be n or only be odd. There's no possibility of falling between. But if you prefer, if that argument doesn't stick with you, just think about normalizing that distribution. Great. Okay, I will erase, and if folks come up with questions in the meantime, I'm happy to answer. Okay, let's talk about, so we still have some issues remaining, one of which I just erased. But I would say one of the main issues remaining is that we ultimately don't care about polymer walks in 1 dimension. This is never going to be a good approximation for a polymer, or I don't know of any polymers for which a 1D random walk would be a good model. We ultimately want this to be a 3D random walk. And what we argued was that we could build a 3D random walk out of the product of 1D random walks. And that would be something like, now I'm going to specify to just 3D. That would be looking at 3 random walks that all have different numbers of steps, N1, N2, and N3. But in the polymer context, all we know is the total number of Kuhn segments. We only know that total number of effective monomers that we have. How are we going to deal with the fact that this requires us to know 3 different numbers? And what we can do again is just lean on the fact that these are very, very long objects. So if we want to know the variance in 3 dimensions, what we can do is we can recognize that for any 3 of these, the variance squared, so this is in the ith direction, that's equal to b squared ni. This is exactly true. And of course, the sum of x1 squared plus x2 squared plus x3 squared. This would then be b squared times the sum of ni, 1 to 3. And, oh, actually, we don't have to make an approximation. I was thinking of a later step. Then this is exactly n. We have exactly what we had before. And that is terrific. This is now, again, the classic result that we have, but now it's extended to 3 dimensions. So now is where we're going to make this approximation in this next step. So now we often are actually going to want to know, this is not going to be good enough for us because, yes? Mm-hmm. Yeah, so now we're going to make that approximation to understand what the ni's are, because we actually do need the ni's to plug into our probability distribution. And so now we're going to make an approximation that these are all going to be the same, rather than doing exactly what you're saying, which would be the more accurate combinatorics, which would be required if you had short chains. So this is a result that we still have. We just showed that it applies in higher dimensions. And now what we're going to do is we're going to assume that it's reasonable to say that all ni's are identical. Assume that for long chains, to a good approximation, you're going to take the same number of steps in all of these different dimensions. Yeah?
I'm a little confused with the previous. So xi square is bni square, that's fine, but the summation x1 square, x2 square is for each xi along the 3 different directions, or?
This is for any direction. And then this is now adding up the fact that I'm walking in x, walking in y, and walking in z, 3 independent random walks. And so if we add up 3 of these together, we would get this sum.
So that b square n is still b square ni in some sense, right? If you.
No, so I'm moving to, so yes, so over here my n was just over here my n was just the number of steps in 1D. This was my 1D n. And now I did this, without saying it, I'm now moving to my real n, my number of actual steps. And so now the n that I was working with before is now my n1.
Okay.
Now I'm adding them all together. So let me write that down. So now let n be total steps in polymer. Total steps in polymer, not just 1D. Yes, and now we're gonna multiply this together. So this then gives us that the sum of these ni's is equal to n. And so this result looks the same as this other result, but I am using 2 different n's, essentially, in those 2 results. So now we are gonna assume for long chains, all ni's are the same. And when we do that, what we can realize is that this can be broken into the product of, if all of these ni's are the same, then we have 3x, it could be x1 squared, it could be anything we wanted it to be, equal to b squared n. If all of these are the same, this will be fine. All of these, the x1 squared, x2 squared, x3 squared will be identical. And so then that means that for our 1D random walk, in terms of the n that now corresponds to the total steps in the chain, we are going to assume that there's n over 3 steps in each direction. It will become an increasingly good assumption as the chains get longer, because you can think about the difference in path length in each dimension as a fluctuation about a mean, and as we're doing these summing up of these random variables, it's approaching its average value according to the central limit theorem. So that will be pretty fast, and this will be reasonable as long as these are sufficiently long.
Also, is there some assumption underlying that every step that you take here is independent of whatever is existing there already?
Mm-hmm. Right? Yes, I will actually, I'm going to write down the distribution and then I'm going to make a comment on exactly that point. I think that's the worst assumption that we've made so far is exactly that. Yeah. This is not what we would call a self-avoiding random walk, and it really seems like it ought to be. And in many cases, it should be.
Maybe slightly related to that also is, if you're thinking of the gel system, you're going to have interactions between, not the single polymer chain as such, but, so is that something that?
If you're having a network, you mean? How do you?
Yeah.
Yes, that will be what we do right after this. And so there are many complicating factors for a realistic gel network. We're going to do the simplest model where we're just assuming a lot more things. We're going to keep packing in the assumptions, and many of them should be questioned. And I think that that's one of the things I hope you take away from this lecture is I think we often talk about these models as if these derivations are it's very good to stay in touch with the number of approximations that we have to make to get to the point where we land, and it works really good in a lot of situations, but there's also a lot of situations in which we should expect it to break. Okay, so now that we have this though, now we can write, now what we're going to do is we know everything that we need to create the full 3D picture here, and just using this 1D distribution that we now have the Gaussian version of before. So we're just going to multiply 3 of those together. And in each dimension, this is the variance. And so what this is going to give us is this beautiful probability distribution, which is 3 over 2 pi nb squared to the 3 halves, e to the negative 3 x squared over 2 nb squared. So this is the end-to-end probability distribution of a random walk in 3 dimensions. So before moving on to networks, I want to comment a little more about a question that I think I have appreciated getting about, is this really a good model for polymers and under what circumstances? So comment on neglecting interactions. So the short answer is this can be really bad. This can really, really change things. And there are many cases, especially if you're in a good solvent where the polymer can really explore all of its conformations very well. Self-avoidance is going to be something that is not, it's a relevant feature, both in the colloquial sense and in the renormalization group sense. It's something that really matters. Rather than go into this more substantially, I'm going to reproduce our argument I found in Rubinstein and Colby that I found to be very interesting to visualize the effects of interactions. So Rubinstein and Colby challenge us to consider a chain of n equals 10 to the 10 bonds. So this is one of the largest DNA molecules that you can find. And so the bonds in this actual polymer are angstrom scale. And so the total contour length would be meter, on the scale of meters. But this is a little hard to visualize, perhaps. And so to get an intuitive sense, we are going to imagine magnifying all of these so every bond is 1 centimeter and talking about how the size of this polymer is going to change as we change the interactions. So for intuition, multiply the lengths by 10 to the 8th. So each bond is 1 centimeter. So now with this, we can consider a couple different cases and see what they mean for how big our giant macroscopic polymer now becomes. So one case you might be worried about is where there's strong attraction between the monomers. That doesn't seem terribly exotic. This can lead to what's called a collapsed globule. In this case, we can estimate the size as just NB cubed, which would be 10 to the 4 meters cubed. So approximate radius for this would just be V to the 1/3, which would be 20 meters. So I'm not so good with my metric, but maybe literally anybody else here could confirm that this is a typical classroom size. So this is for strong attraction. This is how big our polymer is. We can now consider no attraction or no interactions. So the case that we've been considering, this ideal chain limit. This is the random walk. And in this case, R goes as the square root of n times b. This is the square root of time behavior for diffusion. And for our radius of gyration, this is how it should scale. This will give us approximately 1 kilometer, which Rubinstein tells us is a campus dimension. We might instead have just excluded volume repulsions. So these are not massively strong repulsions, just excluded volume repulsions. We end up having a different exponent for how the radius of gyration scales. It ends up going as n to the 3/5 b, which would be 10 kilometers, which in Rubinstein and Colby world is a city dimension. I think maybe that's not, doesn't maybe works better in a smaller city. And then, of course, we can consider polymers with long-range repulsions. Maybe these are electrostatic. And in this case, we expect R to scale as the contour length, which would be 10 to the 5 kilometers, which would be the distance to the moon. So I like this example because I think it emphasizes how weird polymers are and how we can really have this quite strong variance in size. More broadly speaking, a lot of, yes? He scales as, yeah, I mean, I think that you would, for this, long-range repulsions could be many things. And so it's, this is how we're approximating in this case. So for these cases in between where we have no interactions to excluded volume interactions, there's a wide range of things that are possible here. It's typical to write this radius of gyration with this exponent n to the new b, and noticing that it scales from, if we're interested in seeing something that's scaling with this square root, where nu is equal to 1/2, there are many different things where we can consider a solvent that is good versus a solvent that's bad, and somewhere a good solvent will have this nu is 3/5 exponent for a good solvent, whereas nu would be 1/3 for a bad solvent. And so then the theta solvent is somewhere in between, where you get things that look as if there's no interactions, is another case in which the random walk is very accurate. All right, so I may not get to networks today, I'm sorry to say, but let's get at least to elasticity. That much we will be able to do. And maybe if I have 5 minutes, I'll put up my last few notes about stress, which I brought up with me to atone for my sins. Yeah. These I'm just introducing as facts, but those calculations are much more involved. But yes, they're called self-avoiding random walks, and they involve a much more elaborate counting argument, essentially. So I think perhaps there's an expert who could join in on this, but I think that it depends on the concentration of the solution as well as the solvent that it's in. These things, and the temperature, all of these things will depend very sensibly on all those details. So I would argue that it probably could do all of these, but if someone knows the exponent for a typical situation, then feel free to jump in. Yeah. Yeah. And actually, we will see some comments about DNA if we can, when I show the elasticity. So it will not be in its natural environment, though. It's this argument. There's been beautiful experiments about pulling DNA, which have been allowing us to probe some of this entropic elasticity. So let's bring the elasticity back in. That was enough about random walks. We actually don't, if we're just caring about elasticity, it's not obvious exactly how this end-to-end distribution function is actually going to help us. So let's bring in elasticity. So we have this nice function, p of x n, that I'll write now in a slightly different form, where I'll have, let's imagine that I'm still working in terms of counting the number of paths that are falling within a small window and integrating over all of the possible paths that work. So this is just the same rewriting of how we set up the calculation before, but now I'm in 3D. And we want to find the entropy, because this will allow us to find the free energy, because we assume that there is no energy in the system. So the free energy is just minus T ds. Actually, let me say find free energy. F is minus T S. So S is, as before, KB ln omega. So I set this up this way so we can easily find the entropy. So we now can pull out a number of terms. We can pull out KB ln P of x n. We can also pull out KB ln dx1, dx2, dx3. And we can also pull out KB ln d3x omega Rn, or I guess I can call it xn. And now I'm going to split these into two different terms. I'm going to say that these terms over here, actually, I'll do one more thing first. I will take the natural log of my probability distribution from over here. And I will get a term that is 3/2 kb log 3 over 2 pi nb squared. Oh, too many kb's. And I will also get a term that is 3, we could call it, I'll call it r squared for my absolute distance here of 2 nb squared. And then I will also have this term and this term. And these terms, this term, and this term are all independent of R. And therefore, I can group them into a term S naught. So I will rewrite this as 3 kb over 2n b squared r squared plus S naught of n, where these are all my terms that are independent of R. This is still S. And now if I calculate my free energy, I just have minus T times this. So this is 3 kb T over 2n b squared r squared minus T S naught of n. And now we are seeing something really cool. Because what we have found through this series of approximations is an energy that we can forget about this S naught term, but we found an energy that is looking like 1/2 kx squared. It has the same form if x is now this extent. This looks like a harmonic oscillator with this is a spring. We have derived an entropic spring. And this is a great way to think about the actions of individual polymers, is that for these small deviations, we can imagine having an effective spring constant of 3 kBt over nb squared. And this explains many results that we find about polymers and also rubbers more generally. It's why if you have a rubber band and you heat it up, it will shrink a little bit. Things will get stiffer as they get hotter because your entropic spring constant is proportional to T. It also explains a famous observation that double-stranded DNA is stiffer than single-stranded DNA. A single-stranded DNA is stiffer than double-stranded DNA, so the non-intuitive one, and that's because the persistence length of double-stranded DNA is longer. And so that enters in the denominator here, and that leads to single-stranded DNA actually being more difficult to extend, which you can think of it as it has a higher entropic preference for being more compact than a double-stranded DNA will be. So that's something that has been validated with very precise measurements. Yes.
Right. Whereas we've shown that the entropy was maximum for an intermediate length, which would be the rest length of the spring, right?
Actually, that was, so in that toy example that I gave at the beginning, to make it a little harder, I had you include self-avoidance. But if you actually look at the most probable value from this end-to-end distribution, it will also be 0. This is a Gaussian centered around 0.
Yeah, but the average length shouldn't be 0 if you look at all the directions.
Yeah.
Yeah.
If I can comment on this, if you look at the probability of some end-to-end distance, you have to integrate over the sphere, and then you get a maximum that is not at 0. It's not a Poisson, it's a x square exponential minus x1.
Thank you for the comment. So I will briefly foreshadow the next couple things that we are going to do, but we will do them on Friday, which is that we are going, so what we have done now is shown that a single polymer is equivalent to an entropic spring in what we would like to consider. And next time we are going to make the simplest approximation that we can make to create a network of these entropic springs, and then use this to derive a neo-Hookean model and talk about some of its failings, perhaps, and also successes. And then we are going to do a similar argument to get the entropy of mixing to explain swelling. And after that, we're going to have this beautiful full nonlinear theory for the entropy of stretching and the entropy of mixing interacting to lead to stretching. I have 3 minutes left, so I'm going to very briefly write up something that I meant to write up on my first lecture, which is the definition of the 3 stress tensors that we might see. So I won't do this justice for sure, but just to refresh people's memory about the terminology. One thing that we have seen some great examples of is how stress is a really important concept for an understatement. Stress is central to the study of elasticity, and the relationship between stress and strain is called the constitutive relationship. And this is the linear constitutive relationship, which you can find by just asking what are all possible linear relationships between 2 second-order tensors that's invariant under changes in coordinates and these sorts of nice things. And then if you compare this to the linear form of the energy that I introduced last time, you find that the partial derivative of F with respect to the strain tensor gives you the stress tensor as required by thermodynamics. So I introduced our energy density first, but it's more typical to introduce this constitutive relationship first and then get the energy density through thermodynamics. I'll say as required by thermodynamics, which is another way to say that sigma ij and uij, I'm using Landau-Lifshitz terminology, and epsilon ij are conjugate variables. And all of this is just a delight until we start considering large deformations. When you have large deformations, you are now forced to confront what directions you're really talking about, because stress, as we have seen, is a force per unit area. But this leaves a lot to be specified, because in order to figure out what the force per unit area is, we need to specify a vector area element. And we also have to specify a direction of interest. Because as we're deforming the faces of our material element, we're also deforming the, we may want to consider the force that is perpendicular to the original material element or the one that is a warped material element. So specify a direction of interest. And this leads us to, in a very simplified picture, 3 possible choices. So our options are as follows. Option 1, we may choose to measure all quantities in the actual configuration rather than the reference configuration. So this gives us the Cauchy stress, and also called the true stress. And this is useful in a lot of different contexts, but it's certainly what you want to think about if you're wondering if your material is going to fail. You would want to know what the actual true stress is on the material. Another choice that you could use that we saw in our beautiful lectures on beams is you might choose that the vector area element is in reference coordinates. Reference coordinates, but the direction of interest is in actual coordinates. This is something that we saw was very useful for deriving balance laws because it made it much simpler. It's also very useful in comparing to experiments because if you're imagining stretching something, you might want to not have to track how that cross-sectional area is changing. If you might want to consider that. This will give us the first Piola-Kirchhoff stress, which is also called the nominal stress. No, it's not. Hold on, let me do that later. First Piola-Kirchhoff stress. So this is useful for experiments and balance laws, but it is not necessarily symmetric, which is tricky for the kinds of beautiful things that we might want to do with plates, for example. A third choice would be all quantities measured in the reference configuration, or some people say you're pulling back to the reference configuration. In reference chords, or configuration, really. And this gives us the second Piola-Kirchhoff stress. And this is nice and symmetric. And it is also, happily, it's the conjugate variable to the green Lagrange strain tensor, which is our strain tensor with that nice geometric nonlinearity. So it is, it can be very nice to use in a number of applications. So, all right, now I've gone over, but I can sleep easily tonight knowing that I've put these definitions on the board. So maybe we'll encounter them later on as well. All right, happy to take some questions. Thank you all for your attention.
Actually, I want to also make a comment that the first Piola-Kirchhoff stress tensor is conjugate to deformation gradient.
Yes, yes. Yes, and one way that you can, yes, this is a nice comment to include. One way that you can think about these conjugate strains is to think about what variables you had to keep track of when you were building the strain. So this green Lagrange strain tensor, one of the reasons why it was so nice for introducing everything is because everything was in terms of the displacements, everything was in terms of the reference state. And therefore it's somewhat intuitive that a quantity where everything was measured in the reference coordinates for stress would be conjugate to that. And with this deformation gradient, we were talking about a map between the reference to the actual configuration. And so that should prime your intuition to expect first Piola-Kirchhoff, which is also 1 foot in each world going to be able to be conjugate to that as well. So yes, this is a great point. Thank you.
And this stress-strain relationship that we have there for linear elasticity, but there is also a similar nonlinear elasticity equivalent where the left-hand side then becomes second PK.
Yes.
And the right-hand side, epsilon kk is the green Lagrange components.
Yes, exactly. For all of these conjugate relationships that I've mentioned here, they follow the same pattern, the same structure, I guess, as is written here. This is something, if I had given these notes linearly from Monday, we would have F written up right here, so you could see it very clearly. But it's much more obscured in your memory, I'm sure. So, thank you.
I just want to know, so this F that we have built up it's for a single polymer chain,
Mm-hmm.
and it comes out to be half kx square.
Mm-hmm.
And then when we'll go to networks, eventually, then we have all those Fs and all those polymer chains interacting with each other.
Mm-hmm.
So yeah, so that's exactly what I wanted to understand again.
Yes, so we'll do that tomorrow. The short answer is we're going to do the affine network theory, where you're going to assume that all the crosslinks are embedded in essentially a chunk of material. And so we're going to basically set up a bunch of assumptions that allow us to pretend that stretching a macroscopic material is no different than stretching a bunch of these entropic springs. And that is going to be how we approach it. In reality, things like entanglements and the fact that the crosslinks themselves also fluctuate, which is left out of the affine network model, all of these things will have big effects on the entropy and therefore big effects on the actual setup itself. But it's a really good starting point for modeling of rubber-like elasticity, especially for small to moderate deformations. And I think one way you can think about whether or not these models are reasonable is thinking about the assumptions that go into actually deriving the entropic spring constant of this polymer itself. You know, for example, there's a locking strain for these polymers, right? If you really were to pull them straight, they're not going to behave like random walks. You know, as you start putting forces on them, you can start to really quickly get to the limit where a Gaussian distribution is not appropriate for the end-to-end distribution. And that's where that leads you to have, I think, a very clear understanding about when these simpler network models shouldn't be applied. And by extension, neo-Hookean elasticity. Mm-hmm.
Energy minimum for the entropic spring is with a zero resting length, so it's at R equals 0. How are we going to define a non-degenerate resting reference configuration for the material? Everything should shrink to a point now, or am I misunderstanding?
I think that let's talk about it next time as we set up the assumptions that go into the network,
Okay,
if that's all right. For this case, you can imagine this idea that a compact state is preferred, and let's talk more about it when we do networks properly.